Okay, so let's take a look at our calendar. To make up for missing Friday, right? We're just going to pick up on the lesson that we missed Friday. We're going to do related rates today. And then to make up for it, we're going to have to lose the project check-in day. So make sure that you use any extra class time that you have after you finish your activities to work on the project in the upcoming days. And so you can ask me questions then. And then I was going to assign this take-home quiz that day. I'm going to assign it on the previous class with theorems about differentiable functions. So that's it for the schedule. So let's look at our related rates class, class 27. So we're going to learn how to solve problems where several variables are changing at the same time. And these kinds of problems are called related rates. Typically, this is perceived as a difficult part of the course. Okay. Unlike all the easy stuff that came before it, yeah. Okay, so, but if you sort of follow the setup that I give you, it's going to be, that's going to help a lot. So don't try to just jump to solving it, right? Write out all the stuff, all the steps that I'm going to give you, and it will really help. All right, so a boat is pulled into a dock through a pulley that's 20 feet higher than the bow of the boat. Okay. So let's draw a picture of what's happening. So I've got a dock here, and there's like a post up here with a pulley, and then there's the boat out here in the water that's being towed into the dock via this pulley. Okay. This is water. Okay. All right, so this is 20 feet. The pulley is 20 feet higher than the bow of the boat. If the rope is pulled in at a rate of 2 feet per second, now that's a rate. I can't put that in the picture because a picture is a static thing, right? The picture is not moving, so I can't write 2 feet per second on the picture. Okay, so I'll just keep that in my head for a minute. How fast is the boat approaching the dock? So I want to know how fast this distance is changing, right? So let's call that x, right? I want to know how fast that distance is changing when there's 30 feet of rope out. Okay. And then when there is 22 feet of rope out. All right, so in all of these, you draw a picture, a static picture, and you're labeling just distances, not rates. Okay. And you label the distances any distance that's constant you can label, and if it's a distance that's changing, you don't ever put a number in, right? Like the length of this rope, is that a constant or is it changing? It's changing. So I'm not going to put a 30 feet there, right? Because that would indicate that that's always 30 feet because it's a static picture. So I'm not going to put 30 feet there. I'm going to put maybe a z. It's changing, so I label it with a variable. Variables vary. Okay. All right, so now I have my static picture. This is a picture that is static, and the things that are changing I've labeled with variables. All right, so now that I have the picture, I write down what is given to me, right? Or what do I know? And what do I want? Okay, and I'm going to try to change how it's worded in the question to a more calculus notation in both of these things. All right, so what do I know? So what piece of information was given here that I didn't use? The rate, the 2 feet per second. Okay, so the rope is being pulled in at a rate of 2 feet per second. This is the rope, right? How can I translate the rate that the length z is changing to a calculus notation? A derivative. Yeah, what's the derivative of z? How would I write that? dz d what? It's not dz dx because it's the rate that we're changing with respect to what? Time. Yeah. It's not the rate, because x I labeled as another distance, right? So that 2 feet per second, that's a change in distance over change in time, right? So I know dz dt is 2 feet per second. And I have to be really careful here, because is z increasing or decreasing its length? It's decreasing, and a decreasing function should have what kind of derivative? A negative derivative. So this is actually -2, because the length of z is decreasing. So dz dt is shrinking by 2 feet per second, so we, or z is shrinking at 2 feet per second, so its derivative is -2. All right, so that's what I know. And then what I want is how fast is the boat approaching the dock, right? So I would like to know how fast x is changing. So how do I translate to a calculus statement the rate of change of x? Dx dt. So what I want is dx dt, and I want that at a specific moment in time. When? When z equals 30. Yeah, when there's 30 feet of rope out. So we'll just answer that part first, and then we'll come back and do the 22 feet later. So I want dx dt when x is 30. So I've got a picture, and I've written down what I know and what I want to know.
X is 30 when Z is 30.
Z, you're right. Thank you. When z is 30. Good catch. Okay, so now I have two variables here, x and z. They're both changing with respect to time. So what I need is some kind of equation that can relate x and z. Don't think about the rates, just look at the static picture. Is there some equation that we could use to relate the variables x and z? Simpler than trig. The Pythagorean theorem. Yeah. So I know that x squared plus 20 squared always equals z squared. Because this is always going to be a right angle. This pulley makes with the water, always going to be a right angle, even as things are changing. So I have an equation that relates x and z, my two variables. One I know about, one I want to know about. Okay, so the problem with this equation, though, is that it only has x and z, and what I know is dz dt, and what I want to know is dx dt, right? I need some rates in this equation. So we're going to use the implicit differentiation that we learned last class to introduce some rates into this equation. So I'm going to take d dt of both sides, take a time derivative of both sides of the equation. No, it's just d dt, just like last class when we did d dx of both sides. Just take the derivative of both sides. Yep. Okay, so I take the derivative of both sides, and I'm taking the t derivative, the derivative with respect to t, which means t is the independent variable. So what's the derivative of x squared going to be? 2x times dx dt. Yeah, times dx dt. Why times dx dt? Chain rule. X is a function of time, right? X is a distance of the boat from the dock, right? So it's changing with respect to time. So if I'm going to take a time derivative of x squared, think of x as some stuff that depends on time, right? X is like a formula with t's in it. No, if I wrote d over dx, the derivative of x squared would just be 2x. Yeah. Yeah. X is some stuff that depends on time. So the derivative d dt of x squared is 2x times dx dt. And then d dt of 400 is 0. Okay. d dt of z squared would be 2z times dz dt, right? Again, my independent variable is t. So if I'm taking a derivative of these, I'm going to have to use the chain rule, right? The independent variable of d dt, if the variables don't match, if this isn't some t stuff, then you have to use the chain rule because z depends on time. Z is just some stuff that depends on time. So this is going to be 2z times the derivative of z, which is just dz dt. dz dt, I think, yeah, dz dt is the one we know. Yeah, -2. Yeah. Okay, so now I can plug in stuff that I know, and hopefully the only thing left after I plug in the stuff that I know will be the thing that I want to know, and I can solve for it. So I'm going to replace dz dt with a -2. Leaving z blank for a second. Wait, no. Z I know is going to be 30 because I want to know dz dt when z is 30. And then dx dt is what I want to know. So I'm going to leave that as a variable. Okay. How can I figure out what x is? Use the Pythagorean theorem. I'm going to redraw my picture. Maybe not as pretty as the original, but I now know this is 20, z is 30, so this is a snapshot, right? This is just a snapshot of the moment in time I'm interested in. So now I put in the 30 for z. And then I can use the Pythagorean theorem to figure out x. So x squared plus 400 is 900. So x is the square root of 500. I'm just going to leave it like that for now. Square root of 500. So now I've plugged in all the things that I know. There's only one thing left that I don't know, and it's the thing that I want to know. So I'm going to solve for dx dt. So dx dt, that's 60 -120 over 2 square roots of 500. So let's get an approximation for that. Because this is a real life example, it makes more sense to give an approximate speed at which the boat is moving than to answer with a radical. -120 divided by 2 square roots of 500. And I get -2.68. And what are my units on that? Feet per second, yeah. It should be my x units over my t units because it's dx dt. So my x units, they told me all of my distances were being measured in feet. So my x units is in feet. And then all of my rate that they gave me was feet per second. So time is being measured in seconds. So this is feet per second. Yeah, -2.68. Does it make sense that that number came out negative? How come? The distance from the boat to the dock, x, is decreasing. Yeah, so the derivative dx dt should be negative. Yeah. What do you think? Yeah.
I see the 900 in the equation.
I squared 30.
Right, okay.
Yeah. Okay, so that's kind of a complicated example, but it sort of gives you the gist of related rates. There's an example at the beginning of your packet. So this first page is a related rates in class quiz. We're going to do this in class. It's the first page of your packet just so that you can rip it out when we're ready to do it. The next page is a handout, guidelines for related rates problems. And you can use this on your next test, okay, and the in-class related rates quiz. So there's some general guidelines here, and then an example problem of a ladder leaning against a wall and falling. Okay. So a related rates problem is one where you're trying to find a rate of change, and the situation involves different rates of change that are related to each other. Okay, so step one, read the problem, spend some time understanding what's really being said and what is being asked for. Define the variables in the problem. So we had to carefully figure out, okay, what's changing in this picture and label those things with a letter, with the variable. What's constant, label those things with a number. Okay, so some things in a picture will be dynamic, changing, label them with a variable. Draw a picture of the situation. Determine and symbolize what rates are given to you. So write out what's being given, write out what's being asked for, okay, in calculus symbols, right, using rates of change, derivatives as rates of change. Find an equation that relates the important variables. Differentiate implicitly with respect to the appropriate independent variable, which is almost always going to be time in a related rates problem. Okay, so here's one quick example. It's a little simpler than the one we just did. We have a 6-meter ladder leaning against a wall, and then we're going to grab the bottom and slowly drag the bottom backwards. So the top of the ladder is going to move further and further down the wall. Okay, so we're pulling away at a constant rate of 0.5 meter per second. So the bottom of that ladder that you're moving is moving at a constant rate of 0.5 meter per second away from the wall. And then the question is, how fast is the top of the ladder sliding down the wall? Okay. This is the beginning of your packet, page like 2. Yep. Yeah. Okay, so intuition says that the ladder is going to initially fall slowly, right? Because there's a nice sturdy wall that the ladder is leaning against, right? But then as the bottom gets pulled away, there's less and less tension between the top of the ladder and the wall. So it starts falling faster and faster as it gets pulled further away, even though the bottom is being pulled at a constant rate. So, oops. So we're going to let x be the distance between the bottom of the ladder and the wall, and y be the vertical distance up the wall where the ladder sits. So we draw a picture. Okay. X and y, those two distances are changing, right? Because we're pulling the bottom of the ladder, so it's getting bigger, and then y is getting smaller as the ladder falls. So I label those two things with variables. But the length of the ladder is 6 meters, and that never changes, so I label that with a 6. That's a constant. Okay, so even though we're going to look at the point in time when the ladder is 5 meters up the wall, I'm not going to label that with a 5 yet. Okay, I'm not going to put a 5 here. Y is variable, y is changing, so I just leave it a y for now. You put it in when you do the snapshot. Yep. Okay, so then we write out what's given, right? They told me that dx dt is 0.5 meter per second. I wrote it as a positive, right? How come? X is getting bigger, right? X is increasing, it's getting further from the wall, so my derivative should be positive. Then determine and write out what you are trying to find. I'm trying to find dy dt when what? When y is 5. Yeah, you have to go back to the question, right? So the question was, oops, let me go a little further. How fast is the ladder top sliding when it reaches 5 meters up the wall? So I'm looking for dy dt when y is 5. Okay, so my important variables here, my related rates, right? X and y are related to each other, again, in this picture via the Pythagorean theorem. It's not always the relationship, but this is the one that exists here. So I write out x squared plus y squared equals 36. Differentiate both sides implicitly. Take the time derivative of both sides. So the derivative of x squared is 2x dx dt. Derivative of y squared is 2y dy dt. The derivative of 36 is 0. Then plug in the stuff that you know. Often you have to redraw a snapshot in time of the picture, right? So I redraw my picture, I put in a 5 for y, I use the Pythagorean theorem to figure out what x is at that snapshot. And then I can plug in all the variables and rates that I know. So this was 2x dx dt plus 2y dy dt equals 0. So I replaced x with that 3.3 number. Dx dt was a half, that was given. Replace y with a 5. Dy dt is the one thing I'm looking for, right? That's what I was asked to find, the rate of change of y. So that's the only unknown left, so I just solve for dy dt and I get negative 0.33. Think about the sign. Does it make sense that dy dt came out negative? Yeah, because the length, that distance y, the ladder is falling down the wall, that distance y is decreasing. So it should make sense that the derivative is negative. So you can have this little example problem with you while you're working on your related rates quiz and your next test. Oh yeah, the units. Good. Yes. Yeah, that's coincidental. Yeah, yeah. So this is meters per second. Because it should be y units over t units. Y was measured in meters, time was measured in seconds. All right, so we've sort of gone through two examples here. General guidelines, yep. All right, let's do one more. For which one? The what one? Oh, the demo. Yeah, negative 2.68. All right, one more we'll do together. Okay. This is a little bit of a long demo, but I just feel like you really need to see a couple done before you start jumping into them. Okay, so we have water flowing into a cone at 2 cubic centimeters per minute, right? So cubic centimeters is a measure of volume, so that makes sense that we would measure how much water is going into a cup by a volume per minute. So the question is, how fast is the water level rising when the water is 5, 10, 15 centimeters deep? All right, I'm just going to do 5. We won't do all 3. All right, so first thing we should do is draw a picture. Water's flowing into a cone, so I'm going to draw a picture of a cone. Okay, that's a decent cone. All right, so some important variables for a cone would be the radius, the height, and then the volume of the cone, which is based on the radius and the height, right? So this particular height of the cone, they told me is 16 centimeters, and that's constant. The height of the entire cone is 16, and the radius at the top is 4 centimeters. So I can put that in as a 4. Okay. Those things are constant. The size of the cone is not changing, right? But water is flowing in here, and so the water level is changing, as is the volume of water in the cup. So I'm just going to draw, maybe I'll put it in the like blue for water. So here's the water in the cup. The radius of the water is changing, right? As you fill the cup up, that radius gets bigger. Okay, and the height of the water level, the height of the water is also changing, so I'll call that h. All right, so that looks like I've put in all the things that I can. Like I've labeled the constant things and I've labeled the things that are changing in that picture. So now let's write out, what do we know? What do we want? Okay. What do we know? Two cubic centimeters per minute. Yeah. So what is that? What is it that's changing at 2 cubic centimeters per minute? Water volume. Yeah. So we need a variable to represent volume, V. Okay. So the rate of change of volume with respect to time we could call dV dt. And that is 2. Volume as water goes into the cup is increasing, so dV dt should be positive. So dV dt is 2. What do I want? How fast is the water level rising? Which variable in that picture represents the level of the water? H. So I would like to know dH dt when what? When what is 5? H. Yeah. When the water is 5 centimeters deep. dH dt is going to be negative? How come?
Because rate change it's going to be decreasing. The higher it is, the more it's expanded.
Okay, so the second derivative might be negative, but the derivative itself is going to be positive because what's happening to H as you pour water in this cup? What's happening to H? Is it getting bigger or smaller? It's getting bigger, which means the derivative should be positive. What? You're thinking second derivative. You're thinking about how fast the rate of change is changing, right? So it is slowing down, you're right. So the second derivative would be negative. Yeah. Did you see the movie, what was that Matthew McConaughey movie in space? Nope, I'm thinking of a different movie.
Another Matthew McConaughey?
No. A totally different movie. No, the one about dreaming with Leonardo DiCaprio. Inception. Where like you go into the levels and you like can't remember how many levels down you are. That's what you were just doing with the derivatives. Yeah, no, it's totally the wrong movie. All right, so we've got what we know, we've got what we want. Is there a formula that's going to relate my variables R and H and V? The volume of a cone. Anybody know what it is? Well, I think that's the volume of a sphere.
It's H over 3 pi r squared.
I think that's right. I think volume is 1/3 pi r squared H. No reason I would expect you to know that off the top of your head. I didn't. I'm glad Andy remembered it because I was going to Google it. Okay. Okay, good. If I put it on the test, I would give you the formula that you needed. Yeah. Okay, problem is there are no derivatives in that equation, right? So to introduce some derivatives, I'm going to take d dt of both sides. I don't know. Okay, so I take d dt of both sides. Oh, I kind of don't like that there are two variables on the right, the R and the H. I'm going to have to use the product rule if I want to do that, which I guess is fine. I can do that. All right, d dt of v. What's the derivative of v? 1 times dv dt. So d dt of v is just dv dt. It's the derivative of volume. Okay, so let's put a little dot there to remind us that this is a product, 1/3 pi r squared h. And I can treat 1/3 pi r squared as my first factor of my product because 1/3 and pi are both just constants. Okay. And then h will be my second factor of my product. So the product rule says do the first, and you don't do anything to it, you just copy it first, right? Times the derivative of the second. What's the derivative of h? dh dt. So that's first times the derivative of the second plus the second times the derivative of the first. So if I want to take the derivative of 1/3 pi r squared, I'm just going to use the power rule, bring my 2 down, and I get 2/3 pi r times dr dt. Oh, what's the problem here? I have 3 variables. I know something about dv dt. I want to know something about dh dt, but I just introduced a dr dt and I know nothing about it, right? So, all right, we're going to have to find a little way around this problem with r. So I'm just going to X out what I did already. And I'm going to go back to my volume equation. And I'm going to try to write it with only one variable. Okay, R and H are related to each other. Right. Look at your original picture. The radius at the top is related to the height of the whole thing, right? How so?
1/4 of the height.
It's a 1/4 of the height, yeah. Or you could rewrite the height as 4 times the radius, right? But h is the variable I want to keep in this equation because h is the rate that I know about, right? So I'd like to get rid of r. So radius in this picture is 1/4 the height. So I'm going to replace my r with an h over 4.
I'll cross off those 2 r's.
Yep, they didn't work. Yep. Yep, just too many variables. If they had told me something about dr dt, maybe I could have done it, but yeah, first I'll simplify a little bit. So I looked at the big cone and I said, well, the radius at the top is 1/4 of the height, right? Because 4 is 1/4 of 16, or 16 over 4. That same relationship is going to hold down here because of similar triangles, right? You guys remember similar triangles from high school geometry? I know you do. Yeah. Yeah. What?
I was just asking if that's you could just use that any other.
So the reason I'm allowed to use it in this picture is because of similar triangles, right? I've got this triangle here, this orange triangle, right? And then I've got this green triangle, and they're similar, right? Do you remember anything about similar triangles? So that says like radius, right? Like this side, oops, do that in orange. This side to this side, right? The ratio of 4 to 16 equals the ratio of R to H, right? Yeah, they're related linearly by similar triangles, yeah. So you can't just randomly do this. Yeah, you have to have some reason that you're allowed to. And we can because similar triangles have proportionate sides. So then I can solve this little proportion that I wrote, I can solve for r, right? And you get r is h over 4. All right, so we come back to this equation. I've replaced r with an h over 4, and I get volume is 1/3 pi h cubed over 16. And then maybe I'll simplify one more time. So volume is pi over 16 times 3 is 48 h cubed. Much simpler equation. Now I take d dt of both sides. So I'm going to take d dt of v equals d dt of pi over 48 h cubed.
You go back 1 second.
Yeah.
4 over 16. Triangle. Get h.
Yeah. So yeah, just cross multiplied. So you get 4h equals 16r. Divide both sides by 16. Yeah. Okay, so now I take the time derivative of both sides. d dt of v is dv dt. d dt of pi over 48 h cubed, I do the power rule. So I'm going to get 3 pi over 48 h squared, but I'm taking a time derivative of h, which means I got to use the chain rule. So times dh dt. Now plug in the things that you know. I know dv dt is 2. That was given. This is going to reduce to pi over 16. What is h? At the moment in time, I'm curious about 5. And dh dt is what I'd like to know. So that's the only unknown left, and I can solve for dh dt. So that's 5 pi over 16. So that's going to be 32 over 5 pi, which is approximately
5 squared, wouldn't that be 25?
Oh, I forgot to square it. Sorry, yeah. So that becomes 25 pi over 16.
16 or 25.
Well, over here, like when I just multiply this, it becomes 25 pi over 16. But then when I was trying to get dh dt by itself, I multiplied both sides by the reciprocal, 16 over 25 pi. Okay, so 32 over 25 pi. .407. We'll just say 0.41. And what are my units on that? Per minute. I think the time units were all measured in minutes. Yep. So my h units were centimeters, time units, minutes. The right up here?
Yeah, just the whole process.
Sure. So the time derivative of any variable that it is not t, you have to use the chain rule, right? So if this said d dv of v, the answer would just be 1, right? But because it's d dt of v, it's 1 times the derivative for the chain rule. So you get dv dt. And then the same thing with h. If that said d dh of pi over 48 h cubed, right, you would just do the power rule and you'd get 3 pi over 48 h squared, done, right? But it doesn't say d dh, it says d dt. So you do the power rule first, but then you have to multiply by dh dt for the chain rule. Sure. Then we plug in all the things we know, right? dv dt was given. That's one of the things we know from way up at the top. We wrote it down here, right? dv dt was 2. And then we want to know dh dt, so I'm hoping to fill in everything in my equation except for dh dt. And then dh dt when h is 5. Okay, so I replace h with a 5 because that's what I was asked for. Yeah. I don't know. That is scary. So I replaced dv dt with a 2. I replaced h with a 5. The only thing left is dh dt. Just solve for dh dt. Yep.